After our last tutorial about signal flow graphs, which was quite the brain buster, we are now actually going to jump into time response analysis. We're going to talk about transient responses, steady state responses, which I might slip and call them solid state responses. If I do, please ignore. I meant to say steady state responses. And we'll also learn about the different inputs that you can give these time-based, time domain control systems. Okay, so with that, let's jump into what I'm talking about by talking about time response. So whenever we have a system, there's an input and an output, and things don't happen instantaneously. There's always a transition, and that transition takes time. And so that is what we talk about here. And there's two parts of that transition that we need to talk about. And the first is the steady state of when you give a system an input, it will eventually reach a steady state, which is the end goal. And then the other thing is the transient, which is basically what happens between putting in the input and getting that steady state output. So let's use a bouncing ball, for example. If you take a ball right here and then you drop it, let's say at time equals 0, you drop it. And the transient is it falls, bounces a couple of times, and then it stops. So in that system, at time equals 0, with the input of me dropping the ball, the transient response is the bouncing of the ball, and then the steady state response is where the ball ends up and stays until a further input is given to it. And then, since we more talk about electronics and circuits in here, where you would see this on a circuit is with like an RC or an RLC circuit, and you change the voltage on that circuit. The voltage across the capacitor will not instantaneously change from 0 to 5 volts or 5 volts to 3 volts or whatever it is. It will not make that change instantaneously. It'll ramp up or ramp down. And again, there will be a transient time, which is the time where you go from the input until it reaches steady state. And then you have that curve. But then after a certain amount of time, you will get a steady state constant all the way forevermore until you make another input change. So that's kind of your physical example and your circuits example. And again, we've talked about steady state response, transient response, and also that transient time, which is basically the length of time that the transient response is happening. So there's two more terms that you're going to need to know for time response analysis. And the first one is the natural response of a system. And that is when you take a system and with no inputs at time equals 0 and you take everything away, what happens? It took me a while to figure out, like, what in the world is that? Because it's not a very common situation, but this natural response would be like, let's say we have our ceiling with a spring and a weight mounted on the bottom, your typical system, and you pull the weight down, and then at time equals 0, you let go. There's no input, you're not putting energy into it, but there's the natural response of the energy that's already in the system. And again, with circuits, it'd sort of be like, at time equals 0, you don't have a switch open or close. However, you assume that your capacitor is at a certain voltage, and then what does it do at time equals 0? It's kind of like, poof, time starts, what's it doing? And if it's a capacitor with the resistor to ground, then it will dissipate, even though there's no additional input in it. So that natural response is a little bit strange. And the second term that we want to discuss is actually the exact opposite of that, which is the forced response. And that's if you take a system with absolutely no internal energy in it, and then you give it an input, what happens? Going back, it'd be like with the spring and the weight, it's just sitting there at equilibrium and you flick it, or you pull it and spring it, or you push it up, whatever. And then also, if you were to have a circuit, it would be closing the switch, but there's no voltage across the capacitor and there's no current flowing through the inductor to give you some sort of initial response. So you need those two things to actually create a complete story of how a system works, because the full function of a system is the combination of that natural response and that forced response and what happens over time. So again, the full system will be a combination of a transient response and a steady state response, or a natural response and a forced response, which that's two different ways of looking at it, the transient and steady state, and the forced and natural. but they're kind of the same in terms of they both can represent how a system will react. So when you're developing a system, it's actually really important that you do it in a way that not only accounts for the steady state, like what's going to happen once everything settles down, but also includes that transient in the middle. And I was thinking about it, and I feel like a unrealistic but a great example would be getting in an elevator. You get in an elevator on the first floor and you say, I want to go to the 10th floor. You press the 10. Now, if it gets you to level 10, at the end you'd think, okay, what really matters in between? Well, it matters a lot. How fast are you going to be going? Are you going to be going so slow that you die of old age before you get there? Are you going to go so fast that you throw up on it? Or is it going to take you to the 15th floor, then down to the 3rd floor, then to the 15th again, and then back down to the 10th? So you need to have that transient response figured out. At the same time, if you press the 10th floor and you have a nice acceleration, everything goes up, and then you stop and just a beautiful ride, but you're on the 11th floor, again, that's not what you want. So you really need to make sure your systems are satisfying all of your requirements on the transient side and on the steady state side. So if you want to actually see how your transfer function works in the time domain, what you do is you take your transfer function that is in the Laplace domain, you multiply it by its input, and then you get the inverse Laplace of the whole thing. So we'll get into what that input is in just a moment, but that is how you mathematically get something that you can plug into a computer or can manually graph if you're crazy and see exactly how your system should be responding. We aren't going to get into detail on that process in this tutorial. We'll get into it on the next tutorial. But one of the important things here is I said transfer function times an input. And okay, well, what is that input? Now the challenge here is in real life, the input can be extremely random. So if you go back to the spring and weight sample, I could flick it this way, I could pull it and let it go, I could whack it that way. You don't really know what you're doing. And the same with the circuit. Are you going to change the circuit quickly? How are you going to change it? Are you going to make it go up really quickly? Are you going to ramp it up? Or are you going to do all sorts of crazy things with it? And you don't really know. But at the same time, despite the world being very, very random, you can actually kind of simulate most inputs with just 4 inputs. And those are the 4 inputs that we are going to go over. So you know, like, these are the things that typically happen to any system anywhere. So now, get to break out my Sharpie. So the first input that we typically see, and it's extremely common everywhere, is the step input. And so that is where at time equals 0, you go from 0 to 1. It's just a change. So like in a circuits example, that at time equals 0, that's when your switch closes and you have a voltage. You go from no input to an input. This is incredibly common, and like even if you take that ball and you drop it, you're going from up here down to there, and you're basically just doing the inverse of the step function. A lot of things, as you think about it, are simply a 0 to 1 or a 1 to 0 transition. So this is extremely common, and this is called the step function. If you were to talk about this in the time domain, you'd say basically from time from negative, so time less than 0, then your function, and which is for some reason a use of t, equals 0, and then for time greater than or equal to 0, use of t equals 1. Now this isn't super helpful at the moment, it's just good for you to see mathematically what it means, but it is actually very helpful to know that in the Laplace domain, use of s equals 1 over s. So when you have your transfer function and you want to have an input of a step function and see how it responds to that, in the Laplace domain, you multiply it by 1 over s and then get the inverse Laplace of the whole thing. And that is the step function. A couple of small things to note: that capital use of s equals 1 over s. That's just a notation thing, but some people are very particular about it. I am not, unfortunately. I should be more particular about it. But the important thing here is that 1 over s in the Laplace domain will give you a step function where your input goes from 0 to 1. So the step function, again, is our most common input, and you'll see it all the time, and we'll call that number 1, but let's do the second one, which is actually a ramp function. So if we have an input, let's just do an x and y, and this is again in the time domain. A ramp input is like that. So it's basically just your input starts at 0 and gradually goes up to infinity. And you don't see this as often. I think the place you would see this most is in circuits dealing with an integrator, something along those lines, as your integrator goes up and up and up. That was the best example I could think of on the circuit side. And then on the mechanical side, I basically just had, if you're rolling a rock up a hill, not super great. This one isn't used as often as that step response. And there's probably other great examples that I've completely forgotten, can't think of. If you have one that you like, leave it in the comments below. I'd love to hear it. So with this one, you basically do the same thing as before. Your time before 0, your function, r sub t, is 0. And then time after 0, you have r sub t equals k, which is simply your slope, times time. And that's where you get your slope. And so that's what's happening in the time domain. Again, to actually use this, you're going to need to multiply in the Laplace domain. So we have our capital R sub s to say that we're in the time domain. Gives us k, that same k, that slope over s squared. So if we were to put this with our transfer function, we'd multiply k, whatever that constant is, which you should know whenever you're actually doing this. Put your actual constant in there. And then over s squared, multiply it and do the inverse. So that's number 2, which is, I'd say of these 4, the third least likely. Let's do the fourth least likely, or excuse me, yes, the one that I almost never, ever see, which is the parabolic input. So with the parabolic input, instead of just giving us a nice linear growth, it's when our growth curves up like that. And you know, sometimes when you have positive feedback and things grow exponentially, grow out of control, you can get something like this. But this is where time, when you have that less than 0, your p of t equals 0. But then for your time greater than 0, your p of t actually equals k, which again is a constant, times time squared over 2. And that's what's happening in the time domain. Again, you get something to replace that k, and you'll be good to go. Now on the Laplace domain, your capital piece of s actually equals k over s cubed. So that is your parabolic input. Yeah, again, I haven't really seen this much in real life, but again, if you come up with something, leave it in the comments. I'd love to hear it. So that's number 3, but my the one that I've seen the least. Now number 4, saving the best for last. This one you actually see quite a bit, almost as much as the unit step, but not quite as much because it's a little bit harder to replicate in real life. So let me grab my last piece of paper here. And this is our delta function. And this is where you have an input of infinite height and 0 width. So this one's a little bit harder to say what's going on in the time, and also I wrote that in a bad spot. Let's just call this time equals 0 right here. And where here we have if time does not equal 0, then the delta, which that's a lowercase delta, and always looks kind of funky to me, lowercase delta of t equals 0, but then at time equals 0, delta of t basically equals infinity, which seems kind of unrealistic because infinity doesn't really happen in anything we do. But this is the best way to model a really sharp change. So a lightning strike in circuits, or some sort of just a zap when you're doing any sort of ESD testing, things along those lines. In any mechanical system, it'd be like hitting something with a baseball bat. It's just a sharp, really quick, very intense input. And again, it's not going to be a perfect representation. None of these are going to be perfect representations of exactly how the world works, but these are all pretty dang good representations of most of these inputs. So yeah, this is a good representation of any quick, sharp input that just happens and it's over and there we go. Obviously in real life it's not infinitely tall and it's not not zero width, there's going to be some width, but let's not get bogged down by those details and just say this makes the math easy, so you don't want to deal with the real math of having something that actually has some width. And oh yeah, let's not think about that at all. Now, for the Laplace domain, we have that lowercase delta and then our s, and things are very simple. It just equals 1. So it's basically your transfer function times 1, and get the Laverse, good one. Get the inverse Laplace of your transfer function to see exactly how it responds with that delta, that sharp impulse function hitting the system. And that's it. Those are the 4 inputs. We had the unit step response that goes in, and then we had the ramp, we had the parabolic, and then we had the impulse function. That these are the 4 inputs that you can test your control systems with to see how they will react in real life. And that's basically it. So today we just had a very brief overview of what a time response analysis really is all about. We talked about steady state and transient responses, and we talked about the forced and the natural responses of a system. And then we went over these 4 inputs and talked about exactly how they will fit in with our transfer functions. It won't be until our next tutorial that we actually put this all together and get our hands dirty and actually see this in action. And for that, I am actually very, very excited. I hope you like this. If you did, please give it a like, subscribe to our channel, leave some comments below. We love feedback, either positive or politely negative. We also enjoy that. Hope you enjoyed it and learned something. We'll catch you in the next one.